All right, my friends. So I feel good about the whole definition of probability as a long run average. I like that 1 in 6 over time. Um, there are other ways to get probability distributions across to people besides t-tables, and I want to introduce a couple of those in this video. So what I'm going to do is I'm actually going to hide the guts and bring in my good buddy, the pie chart. All right, so what we're going to do is we're going to track the results of this rolling a single die experiment in the t-table, just like we've been doing right there in columns D and G now. But what we're going to also do is reflect those fractions in the pie chart. And interestingly enough, I mentioned the math error. For example, if I roll 2 dice right now, there, I've rolled a 2 and a 4, which should be 50% each. For some reason, the t-table has the math error. The chart doesn't. You can see right now that pie chart beautifully represents that half of the rolls are 2s and half of the rolls are 4s. Now, the one thing that is missing from both the t-table and this chart is the number of trials, which is why I always emphasize, and I've been doing this for those of you that have had me since Math 98, be careful when you're using percentages of any number less than 100. Your audience needs to know what the percentage is out of. Now, we're going to negate that problem in a second because I'm just going to hold down the F9 button and let this thing roll as many times as it can while I'm sitting here chatting about it. Now, what my favorite part of all this is as we roll more and more, and I can't tell how many times we've rolled right now because I've completely, well, first of all, I can't count that fast. And secondly, I've hidden the guts of the experiment. But what's so cool is the pie chart actually speaks for itself. I mean, heck, you really don't even need the P of X column anymore, do you? Actually, you don't even need the entire distribution. The pie chart itself kind of takes care of it for you. I mean, it's hard to notice, but those little tiny slices are moving. Yeah, they're wiggling a little bit as more and more trials are collected and the data is being refined. You can see the little edges moving, but I'll be darned if those 6 pie slices don't all look to be about the same size, which would mean they're all 1/6 of the circle. And this answers a question that I posed in the previous video, and I'll pose again in your homework. When I ask students, what does it mean to have a 1 in 6 chance of rolling a certain number on a die? They tell me, oh, there's 6 sides, and each of the sides has 1 number on it. And that is part of it. But the other part is that all the sides are equally weighted, which means no side is more likely to show up than any other. And that's why I love using a pie chart for exactly this probability distribution. It really drives home that 1 in 6. Okay, so I just wanted to kind of illustrate that you don't have to use the t-table to introduce a distribution. If it's more useful, you can use a graphical method. Let's take a look at one of your homework questions from the last homework, which was rolling 2 dice and keeping track of the sum. Okay, friends, what we're looking at here is an extraordinarily similar simulator to the one we looked at for a single die, except it's rolling 2 dice in cells B3 and B6 there, and then adding them up down there in B9. And then in the table to the right of that, it's keeping track of the sums, anywhere between 2 and 12, as you saw in your homeworks. And then it's going to keep track of the empirical probabilities as we go. And every time I re-randomize the sheet, I'll get a new sum. There I got a sum of 6. I rolled 6 the hard way, 3 and 3. And there I rolled a 3, a 1 and a 2, and so forth and so on and so forth. And if I just hold down the F9 button, I just go ahead and I keep getting all kinds of wonderful results of sums of dice. And what's so cool about this is, as you discovered in your homework yesterday, the probabilities for the different sums vary wildly depending on what the sum was. For example, you probably realized that the most likely sum on a pair of dice was 7. And if you did a little bit of Google deep diving into why that is the case, you realize pretty quickly it's because there's more ways to get 7 than any other possible sum. Another really cool way of looking at this exact same data, though, is graphically. Take a look at this. This right here is a histogram showing the exact same probabilities that we had over there in column G. Notice it's wiggling a little bit. That's because the data is still coming in as we go. But what's so cool is, instead of just being static probabilities on a page, what you actually have are dynamic rates coming in as a result of a study. And as I mentioned before, this is exactly the kind of stuff that statisticians have to do all the time. And what I'm going to do right now is I'm going to let this thing roll for thousands and thousands and thousands of trials. We're going to speed it up and take a look at the results. Years ago, looking at a graph like this, a student that I had in class at the time, we were doing this in class, said, "It's like watching evolution, Sean," which I think is a really cool way of thinking about probabilities. Okay, friends, I'm going to interrupt it now. It's not completely symmetric like you discovered it should have been, right? For example, the probability of a sum of 2 is exactly the same as the probability of a sum of 12. They shouldn't be different even by 1% like they are here. But that's because this is empirical data, not long-term data. And for some reason, I don't know why my poor Excel spreadsheet is having a really hard time re-randomizing right now. It usually works much quicker than this. It doesn't matter. You will, if we let this thing run for thousands and thousands and thousands and thousands of trials, you will eventually see the shape show up, and you'd have a perfectly symmetric left and right side to that graph. Why did I choose a bar graph this time instead of a pie chart? Well, there's nothing wrong with using a pie chart in this situation. There, that's what the pie chart would look like. The only problem is, because some of the slices are so incredibly small compared to the other slices, and there's no legend here, I'd have to add a legend too to actually make it understandable. There we go. But you know what? I agree with you. I think this pie chart doesn't look, yeah, that looks better to me. I agree. The bar chart looks better in this case. Does that mean it's right? Well, I don't think this has a right or wrong answer. I think it's what is clearest. And how do I know that the bar chart is the clearest? Well, after 20 plus years of doing this class, that bar chart, combined with the 2 pie charts at the bottom, which show the individual dice, seems to resonate with the most students. And that, in a lot of ways, is statistics in a nutshell. It's how can you get graphical representations to resonate with folks. Let's take a look at some non-Dyson coins examples next.